present. Okay. Should be visible. All right. Is everyone able to see that now?
I am.
Yeah.
It should be up. All right. Excellent. Good. This wouldn't be anything of a Dr. Wright class without gratuitous dog images. So there we go. This particular dog looks like it's growing succulents by the looks of it. So always good to make sure furniture is useful that way. Okay, chapter 11. So we're talking about applications and processing of alloys. So you guys have had some partial death by phase diagrams, which is okay. There's a lot of useful information there, but something that we'll want to keep in mind. We're going to talk more about phase diagrams, do kind of a quick overview so that you guys have a chance to see exactly what's happening. There's a lot of things that we're going to cover in this particular chapter. So classifications, as well as some common applications, what some of these different material values mean, what some of the different concentrations mean, all of those things. So there are also some fabrication techniques that we'll talk about and some of what that does, as well as some of the heat treatment procedures. So in lab this week, this is really relevant because in lab this week, we're going to be doing heat treatment lab. So there's a lot going on there. This is things that we do to improve the performance of a lot of different alloys, both ferrous and non-ferrous. So we'll talk a little bit more about some of what those things mean. So we're going to cover a lot of what the text is going to include in this chapter. The exception being we're not really spending a lot of time on the different types of cast iron. We're not doing as much in terms of building tractors and trains out of cast iron these days. So that's something it's good to know a little bit about, but most of the things that we're building, we're trying to build in high strength steel and all sorts of other things. So there are more materials than just steel and aluminum. We won't necessarily see all of those kinds of materials, but we will get into some of it, and this will help kind of get a little bit more of the information in front of you guys. So steel versus iron is another big major topic from this, as well as some details about what some of the non-ferrous alloys are. There's a few that we use pretty commonly. There's a lot that we use in different types of tooling and things of that nature. So there's a lot that that goes into understanding how these different metals and how these alloys behave, why they behave that way. And it ultimately all comes back down to molecular structure. So phase diagrams, you guys have probably all seen at least a couple examples by now. So I know that was kind of maybe a weak point every semester, is understanding what the phase diagram means and how to read these. Each of these different phases is a unique material with a different kind of composition. So we have regions that are defined by the melting temperature and the weight percent of carbon. We also have, depending on the complexity of the material and the number of different phase envelopes, which is what like the austenite and L phase for liquid are. Each of those phase envelopes is going to be different for every different type of material. So whether it's steel, whether it's aluminum, there's all kinds of different phase diagrams. This is also only a small portion of the iron carbide phase diagram. As you increase carbon, you change lots of properties, but for a lot of things, we focus on just this small section of the graph. So higher temperatures, everything's liquid. Does anyone remember offhand what the eutectic definition actually is, or what that means, why it's significant?
Isn't it the point where substance goes from a liquid to a solid?
Yes. Yeah. So the thing that's special about the eutectoid is, or the eutectoids is a little bit different. The eutectic point, that's the lowest common melting point of a material for a given for any given composition. So that's what the eutectic point means. It's the lowest common point of a phase transition. In this case, for the austenite side, there's another phase transition as it continues to cool and recrystallize. There's these two different phases, and the austenite only phase disappears at that point. So the lowest temperature point, that tells you the composition for the eutectoid. So every bit of data that we have ultimately builds this picture for us that we have a lowest common temperature at which point another phase transition happens. The final phase transition, that's the eutectoid. So that's the easiest way to remember those, is thinking of those as being the bottom of the valley for a phase transition. So anytime you're confronted with questions about that, because all these different phase envelopes are describing some regions, and we add in these lines to help understand what happens. And so these gamma crystals tend to reform into various ferrite or alpha crystals plus carbide below this 727C. So each material is going to have something like this. If there aren't as many different types of crystalline states available, you may not have the same degree of eutectic and eutectoid, but we won't talk in too much detail about that. This is just meant to kind of cover a little bit more of the details that are necessary. So there's also these two major classifications, ferrous and non-ferrous. So these are ferrous, you can think of as these are the materials that are magnetic. So one of the old adages from welders is, if you can stick a magnet to it, you can weld it. That includes some of these cast irons, as you'll see in a second, as far as which region are cast irons. The downside is cast irons are much more fragile in a way. So they're very hard, but they're also very brittle materials. So you can weld the cast iron, but it's really tricky to do. So even though they're chemically so similar, their material behaviors are wildly different just because of a couple percent difference in carbon. So that carbon content is actually really, really important. That's why it's so important that we're going to see it actually goes into the naming schema for different types of materials. So non-ferrous, non-magnetic, those tend to be, to some extent, those can be harder materials. They tend to be more brittle. Lower carbon content tends to be a lot softer. And that's why this region is so important for the overall phase diagram. So steels are anything below 1.4 weight percent carbon. And this is why, like, the austenite regions and things are so important, so that we understand what material behaviors we can expect. when you get above those significantly, you get into higher carbon steels up here. Cast irons start above 3 weight percent. So this center region in white is kind of more what you can think of as your tool steel region, and cast irons are even harder up in this range with the 3 to 4.5% weight carbon. Some of the key factors there are just that the materials behave hugely differently because of how much of this iron carbide or cementite is present. So more and more percentage of cementite, the harder the material is, and typically the more brittle it is. So the microstructure here is a very important aspect. And so for there's going to be ferrite and then a combination of graphite and cementite. And that's what this region down here is telling us, because the pure ferrite is here on the left and the cementite is all the way on the right side. So anywhere in that region, depending on the weight percentage of carbon, as we cool down from liquid phase, if we were at 2%, we're going to transition just through the very, very edge of this austenite region. And then we'll have ultimately a lot of alpha and cementite at the end. But depending on how the material is worked, if you have different, if you're laminating different materials, if you're forging them, you get to have a lot of different kinds of examples there of what the different layers of materials do. So I'll see if I can incorporate some of those kinds of information into lecture as well. So steels are where we spend a significant percentage of our time. The low alloys are going to be below the 1.4. The high alloys are going to be above that. So this is where you start getting into like I said, much more the tool steels. So plain steel, something like a 1010. We're going to talk a little bit about the nomenclature here in a little bit. The key thing to know for now is that second set of numbers, the second pair of numbers in steels, tells you something about the carbon content. So 1 versus 4 versus 95, and we'll talk a little bit about what that looks like and why. When you start getting into the higher alloys, anytime we're using a combination of chrome, vanadium, you may have heard of vanadium steel or chromoly steel. Typically a chromoly is going to be somewhere up in the higher regions. So that's tooling, getting closer to almost stainless materials. Typically, sometimes it'll be in this kind of range. There's a lot of different combinations of things that we do. The more chrome, the more stainless the material is. So high chrome content changes things. These are very corrosion resistant. So depending on what range you're in the low carbon, the medium carbon, or the high carbon content, you really don't have too many extras, at least in the case of the 10 series steels. You're not including any of these other atoms in the alloy. These low carbon steels are also, so this is like one of the jokes from early staff members used to be that they would get steel for the lab and we would ask them what grade it was, and they would say, you know, it's the steel kind from the hardware store. Like, what are you asking me? That was a really frustrating conversation because not having a sense of what the steel is. You'll notice this says no hardenability. You really can't harden those kinds of steels. So you can use it in structural, you can use it as sheet metal. There are automotive applications that use these, especially older cars use a lot of these for body panels and things. It's softer, it's easier to shape, but yeah, there's a lot of other issues. So there's a couple variations, like a 4310 is kind of a sort of cheaper hardenable steel. That's why it's used for bridges and towers and pressure vessels, tanks. Those are like tanker trucks and things can have this kind of steel in them. They are at least hardenable, and there's some degree, because of the addition of the chrome and some of the other things, there's a degree of resistance to corrosion, but not much. The tensile strength is not great of these. They're okay. The tensile strength of these soft steels is not very good. There's actually some aluminums that are stronger in terms of tensile strength, like, for instance, aircraft aluminum is stronger than in tensile strength than some of these low carbon steels. So the percentage really heavily matters and hugely changes the way that these things behave. So higher carbon content, medium carbon content, this is really more the range of the heat treatables, the 1040s, 4340s. This is where you see a lot more bolts and fasteners, crankshafts, and steel things that are heavy and need to take a lot of abuse for their entire lifetime. Hammers, those sorts of things, right? Few things actually take more abuse than like a sledgehammer, right? So we have to use a little higher carbon content in those, but we don't need to add in extra alloys because you don't need a titanium sledgehammer. Like, that would be a little silly. You actually want the mass, the weight, and the durability of a steel in that application. You don't necessarily want to go with a lighter alloy because sometimes you want enough strength and durability to be able to take repeated blows, and so that works really well for those kinds of things. So crankshafts take a lot of abuse in kind of the same manner that hammers do. So those have to be very, very durable. So these are commonly used in tools and all sorts of things. So gears and wear applications, 4340. So addition of the chrome, nickel, molybdenum make these very highly hardenable, and they're very, very good in tensile strength. So they're really good in areas where you're going to have a lot of sharp loading of things, and so gears and high wear applications, very hard surfaces are needed, and that's where this material comes in. So there's a lot of things that help there. So some wear applications are where you might see something like a 1095. These are where you have kind of almost like a sacrificial layer of steel on something. So there's a lot of applications of these. Once you get a little bit higher, you're getting into this tool grade up around about the 1.4 range. So the 4190, really, really good stuff. Very high degree of hardenability. The reason there being, when you're up above the 1.4, you're transitioning through a lot of this austenite region. So you can change the ratio of of carbide, depending on how you heat it, how far you heat it, and all of those things. Typically, we don't go all the way to liquid. There's a bunch of reasons why. And locally, some of the crystals will rearrange. You can have some local shifts in that phase diagram. So we'll talk some more about that a little bit later. So these are great for things like cutting tools, which need to have very high tensile strength, very high hardenability, right? Think about a metal saw blade that's supposed to cut through concrete or something, right? Like something that has to take tons and tons of abuse. It has to maintain a really sharp cutting edge through lots and lots of material. And this is where you get lots of much more carbide in that range, and that carbide really helps. And sometimes we're even coating those in another type of carbide material like titanium carbide. So when you hear titanium cutting edge or something like that for tools, that's what they're talking about, is a titanium carbide coated material that's probably a base tool steel like this. How professionally that was hardened probably depends on where it was manufactured and how, but that gives you the ability to have really, really good cutting bits, cutting drill bits and things of that nature. Stainless are the high alloys, so much higher percentage, above a couple percent of other stuff in the steel. Get you into some of the different grades of stainless. So 304, 316, 409, those are some of the different varieties. Hardenability is kind of tricky with stainless. So the reason that you know some of that is, think about, for example, like a generic cheap set of kitchen knives from Walmart, right? How long does it take for a really cheap kitchen knife set to get dull? It happens pretty quickly. There's not a lot of hardness to that cutting edge. Whereas people spend, sometimes maybe you get a set of 10 knives from Walmart for $100 or something. I don't know. With inflation these days, it's probably like $300 now. There are people who will turn around and buy professional chef grade knives that are going to be more in this tool steel range. So they're going to be stainless, but they're going to be closer to this tool steel. So they're going to have a little less chrome in them, a little more maybe vanadium, molybdenum, or tungsten. Tungsten steels tend to be just awesome. So there's a lot of really, really cool stuff that you can do with them, but they're going to tend to not be really high alloys. They're going to be lower alloys that are harder and can maintain that that cutting edge longer, but at the expense of, now you don't have the same corrosion resistance. So, and there's certainly other high temperature applications for these, especially in terms of turbines and furnaces. So exhausts for even your common household dryers and things. Those, at least code for today, not not back in the 60s or something like that, but code for today is galvanized, doesn't really cut it anymore. The safest applications are stainless steel for the exhaust for a lot of those kinds of burners and things. So you have increasing strength, and you have, let's see if I can pull it over here. There we go. But you have a cost trade there of the decreasing ductility. So these materials get harder and harder and harder, but then they have a tendency to want to break or shatter because they are more brittle, they are less ductile. So you wouldn't come up here and pick a tool steel for something like a spring. That just doesn't make sense. So there's a lot of good utility to each of these materials. So naming schema are important. So this is based on the AISI and SAE standards for nomenclature. 10 and 11 series are going to be plain carbon. 11 series, they've added in some sulfur to try and make machinability a little bit easier. Those are not things that are needing to be hardened for particular applications. The moly content, so 40 starts at around 0.2 to 0.3. It can be a 41 or a 42, depending on what else is in there. 43 tends to have nickel, chrome, and molybdenum. So all of those, and it's in different ratios. And this is part of the reason why it's a grade. It's not exactly specific. This is part of the reason also why there's a big difference between steel coming out of an American mill in Pittsburgh and steel coming out of the Pittsburgh province of USA, China, or something, right? Like there's where all the Pittsburgh tools are made, right? Because they're not actually made here in the US. Those materials and those differences are actually huge in terms of the way a steel behaves. So steel from different countries can even have different grades. And this is part of the reason why people are so hung up on some of the Japanese steels and things. They tend to pay a little bit more attention to making sure ratios are precise, so they get a little better consistency overall. And that really helps with tooling especially. So the 44 series is much higher in molybdenum. So a lot of the like chromoly type steels, those are going to be typically in your 43 series. And then the 2X figures are weight percents in carbon. So some of the earlier examples that we were looking at, 0.95, 0.9, 0.4, and 0.1 tells you where they're at in that range. But understand that you could also have like a 1050, 1060 steel or something like that, right? But it's far less common. 1040 is a lot more common. So there are ways to get custom ordered steels, but it's really hard to do so. More than 11% chrome is the stainless. So there's also other alloying elements, and depending on what the end application is, you need these different grades of stainless because of particular temperature characteristics. They have differing amounts of chrome as well as typically nickel and molybdenum. But chrome is the primary thing that distinguishes a stainless. So higher weight percent, like a 434 stainless tends to be fairly expensive. A lot of stainless jewelry will tend to be like 304, where it's just barely a stainless steel. It's very easy to scratch, right? A lot of stainless steel sinks and appliances are going to be that lower grade. So those are important things. So for instance, something like a 1060 steel is going to be a plain carbon series with 0.6, and it's going to be mostly iron with just a little bit of cementite in there. And that's how we know some of these things. Cast irons are a little bit different. They're much more commonly very high carbon content, because for most of the applications you want something that's very easy to cast, but also that means you need a low melting point. So going back to see our diagram, right? If I could melt this and cast it at around 1200 degrees instead of having to kick it up to 1600 degrees, that would be preferred, right? So the lowest melting point is where a lot of those cast irons are made, just because they don't have to go as high in temperature to be able to reach those regions. And that's why that eutectic point is so important. So they tend to be very brittle, especially because of that additional content. So I know there's been a couple recent video games where they use cast iron in body armor, and there's been some examples of those in Western movies and things. Sure, that's going to help slow something down, but these are brittle materials. They're going to shatter the instant something at really high velocity hits them. And so again, that's Hollywood doing Hollywood things. Yeah, maybe don't take video games advice on body armoring literally. It's a good rule of thumb. I'm sure a few of you are familiar with what I'm talking about. I haven't been able to play video games for probably about really the majority of the last 10 years or so. So yeah, there's been a couple changes since then. Most of these are going to be iron carbide. There's going to be a lot less of the alpha iron, but there is also going to be a lot of just graphite, just carbon together. So those things deposit in a couple different ways, and that's generally pretty slow. So there's a slow cooling that happens, again, to conserve the energy of manufacturing for the sake of simplicity. So here we're showing a little bit more of the diagram up here, because up above this this range, so especially at above the 5-6% range, you're very much into the liquid and graphite phase. So there's a lot of graphite that forms, and that's just literally carbon powder that's collected together in the material. So it can't be very strong because there's no other bonding agents there. So your crystalline structure looks hugely different. And graphite is the same thing that we use for pencil lead, right? Structurally, graphite's not a great material, not very good material properties, at least for building anything, right? Works great for pencils, will continue to work great for pencils. A lot of useful applications for it, but not structural ones. So it also helps when there's a little bit of silica in there, so a little higher than 1 weight percent. Silica is often present in the casting process because a lot of those molds are compacted sand molds in different varieties, and so they cool very slowly, absorb some of the silicon from the sand in the mold. And that's part of what helps to increase the graphite formation. This is kind of what that looks like in terms of cast iron. So there's different types. There is a version of iron that is a little more ductile, so it's lower in carbon composition. So it has these dark graphite regions, and it has these brighter iron regions. So a gray iron has a lot of these graphite flakes throughout. It's very weak, and it's brittle in tension. So this is why you don't see like cast iron pillars made these days. And when they built stuff out of cast iron to be structural, it was always big and massive and heavy. And so cast iron gates and things, they're just massive structures with obscene weights because they had to be thicker in order to be stronger in all the right dimensions. So there's a few instances. So the ductile iron is also important. This is one that They have the addition of a couple other elements. So magnesium or cesium are fairly common there. And the graphite shows up as nodules rather than as flakes. And that tends to be an important distinguisher because of the way that some of these materials are going to behave. So those nodules, you can imagine, are a lot easier for, if you think of the grains trying to slide past each other, the nodules are going to almost roll more like ball bearings, whereas the flakes are going to resist the movement of grains past each other. And so they're going to want to just separate along those grain lines and fracture or crack in random patterns. And that's exactly what it does on the macro scale. So good for vibrational dampening in the case of gray iron. So gray iron is pretty common, like things that you see made of iron at Harbor Freight, for instance, are probably all going to be this gray iron type. So good wear resistance, good vibration dampening, really strong in compression. So you can put a lot of weight on them. And that's why Harbor Freight gets away with things, is that material is pretty strong, but not in tension. So there's a lot of applications, like you wouldn't want a cast iron chain. That would be a really terrible idea. They used to make them, but that was because they didn't have a lot of other choices in the steel development early on. So the ductile iron has a lot more perlite often, and so it's stronger but less ductile, and that allows it to be a little bit malleable compared to some of the other things. But the compacted graphite iron, those are really good for thermal conductivity and good resistance to thermal shock. So a lot of really high-end cast iron cookware and things are going to be something like that. They also have lower oxidation at elevated temperatures, so that's another problem that you tend to fight with cast irons, is that tendency to rust or degrade. So the higher the grade, the less there will be. Some more types of iron, especially for like white iron, less than 1% by weight silicon, perlite and cementite. So you can look for kind of this zebra striping pattern that's distinct. That's always indicative of a very strong material. But if there's a lot of it, like there is in this image, very, very hard, but also very brittle. So in this case, based on looking at the grain structures, there really is not going to be a lot of easy movement along grain boundaries. These are not usual shapes. They're not rounded at all. And so those grains are not going to want to slip and slide past each other. So again, very hard, very brittle. It'll just tend to fracture along very jagged lines, which is what you see in the actual material. White iron is treatable, so you can regrow different crystal types. And so these are what are called rosette formations of the graphite. So more flowery looking. These have a reasonable strength, but also pretty good. They have some ductility, and that's really, really important for some of the applications there. Because we want to have some materials that aren't just exceedingly brittle in this region because of their high durability and relatively low cost to manufacture. So here's kind of what a production breakout looks like. If you reheat and hold at 700 for 30 hours, so you go really up high in temperature and hold for several hours, depending on how quickly you cool it, what will happen is you'll cool it down and follow a you'll sometimes follow a grain boundary through, or you'll follow one of these phase lines down, and then follow down again as you're cooling in the region. So depending on how quickly you cool, you can get perlite and graphite, or you can get alpha and graphite. So if you just cool very slowly, if you cool very aggressively, which is like quenching, you get more of this perlite. So it's a mixture of the grains and some of that carbon together. So in the commercial cast iron range, like the white cast iron, so at the lower end, you have a fast cool. So something like a quench is going to get you closer to this. So you have a combination of carbide and perlite. So perlite, again, being that zebra stripe pattern. The gray cast iron that is perlitic is moderate cooling rate. So a little bit faster. So maybe aggressive. It may not be like a water quench or an oil quench. A lot of times an oil quench is used instead of a water quench so that you don't have corrosion on the surface, but you do cool things down. That gives you the opportunity to deposit additional carbon from the oil sometimes into that surface. The gray cast iron that's perlitic is going to be very, very common. And then slow cooling is going to result in a lot more of the alpha and the graphite instead of perlite and graphite, because you need to kind of quickly, you can think of it as trying to sort of trap the carbon and the iron together. If you don't do it quickly enough, you don't trap the carbon, and so it automatically will kind of get pushed into the graphite flakes. And the graphite flakes are not great for those. And so the GF is graphite flake, the GR is the graphite rosette, and the GN is the graphite nodules. So that's what the nomenclature means. So again, more of the magnesium and cesium. Moderate cooling gives you more of the perlite because you're trapping some of that carbon along with the iron. And the slow cooling gives you back a lot of alpha. And this gives you the ductility. So perlitic ductile cast iron is actually kind of a really great material because you have elements of hardness, but also ductility. So this is one of the nicest examples of cast iron for a lot of applications. There are some limitations though, so things that we want to be mindful of. The steel is pretty high in terms of density. A lot of the ferrous alloys are going to be in this category, so steel being one of those. The low electrical and thermal conductivities, yes, steel does conduct, but there's a reason why we don't use like steel wire, for instance, typically for conducting. It's very low electrical conductance, so it really doesn't help. So it actually makes better heating elements because it's resistive to electrical flow, and because its thermal conductivity is a little bit lower. So this is why like electric ovens, electric heating elements, often you'll see are going to be steel. They're going to be a little bit higher carbon steel, kind of getting closer to the cast iron almost, mostly because that additional carbon is additional resistance to the thermal conductivity and electrical resistance. So works great for a heating element where you want something that's resistive to the current, but also needs to be strong and be able to take impacts. And that's why you don't see a lot of copper heating elements, for instance. So the poor corrosion resistance is also a key kind of Achilles heel to these. So without any kind of chrome or anything else to be a defender against oxidation, you end up with a much different kind of behavior from the material. So the plain carbons are using a measurement called Siemens per centimeter. So this is a BTU inch per hour square foot degree Fahrenheit. So it's temperature dependent, it's area dependent. And what they're doing here is basically dividing out the area so that you can just understand per the thickness of the material. So instead of looking at the volume, per the thickness of the material or the distance in one direction through the material, how many BTUs is this absorbing for a particular temperature? So looking at it relatively, pure aluminum, 38 times 10 to the 6th compared to just 6 times 10 to the 6th for plain carbon. For the aluminum, it's a little bit, the aluminum alloys, it's a little bit less, but then you see the lowest thermal conductivity of stainless. So stainless being the one that we use often for high temp applications because of that difference of being able to cut down on thermal conductivity. So very, very low. So converting that or that the electrical conductivity, stainless is really low. Similarly, the thermal conductivity, it's higher in steel, it's lower in stainless, much, much higher in aluminum, even the alloys. So there's a lot of key parameters there that we want to know. So, and this is all referenced at about 22 C. So more or less what you consider to be room temperature. Non-ferrous alloys, there's kind of a lot here. So we'll spend a little bit of time here. There are some high strength ones. And so those would be something like copper beryllium. These are non-magnetic and non-sparking. So these are specialty tools used in highly charged environments. Those are very expensive, very difficult to get a hold of. Bronze and brass are really good alloys used for a lot of things. So brass has zinc. There are some it's a substitutionary impurity and it's done purposefully, whereas bronze has got tin and aluminum and silicon and nickel. So bushings, there's lots of wear applications where bronze is used because it's softer than steel, but still has a reasonably high hardness and can be very compliant. So a lot of bushings are made that way on purpose. Brass has a lower, it does have good corrosion resistance, but it's a lot of like costume jewelry, materials going into coins and other sorts of things. Brass is fairly common for that. There's obviously a lot of other kinds of applications. So brass can be actually a pretty hard material as well. So and it's fairly easy to work with in terms of machining and other things. So that's why it's used for so many applications. Titanium alloys are another example of non-ferrous. So all of these are non-magnetic or non-ferrous. So titanium, really low density, almost half that of steel. So that's why it's used in a lot of things. But it's also very reactive at high temperatures. So there's a lot of space applications and things where this is an exceptionally useful material. We also use it sometimes titanium alloys, titanium carbide, for instance, as coatings for some of those tool steels and various cutting tools. Just because, or even more common than that is titanium nitride. So nitrides tend to be some of the hardest of the coatings. Really, really durable stuff. Really works well. So that's that kind of goldish color is titanium nitride often. It's really, really a durable coating. Very high surface hardness, very great wear characteristics. So a lot of useful applications for those. Aluminum's lowest density. So a lot of people think that maybe titanium and aluminum have similar densities, but aluminum is almost half that again of titanium. So lots of good applications there. More copper, magnesium, silicon, manganese, and zinc in different ratios. And they are sometimes developed as a solid solution, sometimes precipitated for strength. So specifically like aircraft parts, those sorts of things. Aluminum cans are also usually a specific alloy. I don't know offhand what that is, but they're designed to be structural and use a minimum amount of material so that shipping costs are low. So there's actually a lot of engineering that's gone into the shapes of those and how they work as a pressure vessel and all those sorts of things, being such a thin wall. Because they're, if you think about it, an aluminum can full of beverage before it's opened, it's actually a pretty strong structural unit. As soon as you open it, you compromise that ability because it's designed to resist change in shape under additional pressure, which is really important. Magnesium alloys are very, very low density. So this is why they were used in some applications for automotive things. The trouble is it's very easy to ignite magnesium alloy, and they actually are pretty highly flammable. So in high heat applications, magnesium is actually not really great, but they are used in aircraft. They are used in construction of missiles and some other things. There are some refractory metals, so really, really high melting temperatures. So nubium, molybdenum, tungsten, which is the W, as well as I can't remember offhand what TA is, but it's in the same transition metals region of the periodic table. Basically, what those are doing are using their extremely high melting temperatures to be, depending on the alloy, they can also be very hard. So I tend to run, when possible, I tend to run like tungsten nozzles, which are really, really awesome for printing. And then there's some noble metals, so platinum, gold, silver, a lot of these precious metals, those are extremely oxidation resistant. There's some other metals like that, but their main characteristics are being very hard to tarnish or corrode. So there's a lot of important applications where that's the case. Fabrication of metals and looking at how things are done. Forging is a really good example. So casting is another one. There's a lot of intricacy to the forging process. There's a lot of knowledge that has to go into it. Casting, there's also some kind of hybrids of those two techniques where they're flow forming under pressures, and so they're not doing the traditional operations, but they might be casting under pressure, things like that. There's also some big differences in hot working versus cold working. So those are some of the ones that we really have to pay a lot of attention to. The hot working is important because it allows for large deformations. So especially something like a hot rolling process. So you've likely heard of either hot rolled or cold rolled steel in the context of especially like tubing. So a lot of different safety applications, whether it's in motorsports or other things, require some kind of a roll cage. Typically, those roll cages, they mandate be made out of seamless tubing, so tubing that hasn't been welded on one side. And very often they required those to be either they require them often to be cold rolled. So a cold rolled or DOM for drawn over mandrel. They do this kind of process where they're changing the shape of the material. So you have coarse grain structure, then you flatten it with a couple of rollers, and then you get some recrystallization and growth of new fine grains. The finer the grains, the more resistant they are to movement. The bigger the grains, the less resistant they are. So the more ductile the material here, the harder the material here that comes out. So especially in the case of cold rolling, you can think of it as literally just smashing these grains together, and you compress them in a way that it makes it very strong in this direction. So not necessarily any stronger in the tensile direction, in tension, but it does make it stronger in terms of compression in the same direction that you're doing the rolling. Because you're smashing the grains together, makes it much harder for those grains to move around at that point. The cold working is small deformations. There is a strain hardening that you're doing. So you guys have talked about the stress strain curve. You're stressing the material in an axis to do cold working. So this is cold working is also the kind of thing that if you've ever grabbed a hold of material, even something like the top of a Coke can, or an energy drink or whatever, you pop the tab up and then you work it back and forth and then pop it off. That's cold working the material. You're strain hardening those grains until it just fractures and comes off. So those are small deformations. And now you guys know you can go have a really cool conversation the next time somebody opens a can of Coke in your presence. It goes great at dinner parties. So there are other forming operations. So drawing, like that DOM example, drawn over mandrel, as well as extrusion. So extrusion is a pretty simple one to envision, especially for those of you guys that have gotten to use a 3D printer in some capacity. Those are extrusion-based machines. So you start with some kind of rough stock and then form it into a final shape. And lots of different examples of what that can look like. So forging or hammering and stamping has a blank material set into a die. A high force is created, often at elevated temperatures, just to improve the malleability of the material. And that works fairly well. So then you also have examples of like hot or cold rolling. So I-beams, rails, things that need to be hard in a specific direction. Sheets and plate steels are all made this way. just because it makes them strong in one direction and not necessarily strong in all directions, but strong in an important direction. So sheet steel would be a lot weaker if it wasn't rolled, whether hot or cold, depending on the end application. So the drawing are rods, wires, tubing, those sorts of things. So the die has to be really well lubricated and clean. It's really, really important because you can imagine that sort of force of pulling on the tubing from the blank stock. That's very hard on the die itself. So the dies have to be a very hard surface in order to reform the material into the new shape. So your typical roll cage material is going to come out from a process like this. Extrusion, you have some sort of in the case of extruding steel, copper, aluminum, stuff like that. This is easier done with materials that are ductile. You're not going to see extrusion for other processes. You have some kind of removable die. You have some sort of die holder and something that pushes the billet of material through the extrusion die. You can imagine this is for a material like aluminum at an elevated temperature or copper. This is great for being able to make something like rods and tubing. Not so great for other kinds of geometries. So typically this kind of process is going to be extrusion. It's going to be circular, rectangular, square, something like that. So that's how those are made for the most part. Alternatively, sometimes someone will extrude a shape or they will roll a sheet lengthwise and then weld it. And that's another way to make tubing. So a lot of common exhaust tubing is made that way. So it's rolled out into sheet steel, then it's formed into a circle by rolling, and then welded along a seam, which is fine for an application like that where you're not, there's not a lot of structural importance to it. It's just a pipe to carry some gas to some other place. Casting. Casting is a really awesome operation. Molten metal that's heated in a crucible, usually using some kind of a furnace, is able to drop into a mold. They're typically common and inexpensive, so a lot of aluminum casting is done for a lot of things, and it gives a good production of shapes. They're general shapes. Sometimes it's hard to get a lot of really exceptionally detailed castings. You can, but it's there's some tricks to it. These are typically weak products because casting is not it gives you a lot of possibility for internal defects, and that's really what the main weakness of casting is. So non-uniformity of the material creating weakness in the product. Any of those defects introduce fault propagation opportunities in the material, and so that crystallinity comes into play really heavily. So for brittle material, it's a great option because it's really hard to machine something out of brittle materials. Doable, but very difficult. So a lot of machinists don't like to do that. Casting works a lot better. Especially when you look at what happens. So this is an example of the stages of solidification in a casting. You have solids close to the mold wall, and that's it. So you're at the melting temp, and then as your material starts to cool down below the melting temp, especially at the mold wall, as the mold itself starts to heat up, you start getting some solids. So you'll get liquid metal with just a fine layer of crystals around the outside. Then you'll start getting some columnar crystals starting to grow in the interior of the casting. And then you have the these equiaxed crystals. So these are these are equilibrated to each other. So they're a lot more uniform in the center. But the other thing that this doesn't really show is the material will shrink very often as it cools. And so you'll get divots in these examples. You'll get divots in the material, or you'll lose some of the volume that you had at the liquid temperature. So it may still be hot at this point, but it's all solid, and there's different types of crystals at different regions. And that's why it gives this such a high non-uniformity in strength. So that change in volume becomes significant and on solidification. So you have a reservoir typically. So this is for more routine casting operations. And you have some kind of feeding operation. So runner to bring the metal into the mold, and then some kind of control gate or control mechanism. So the very commonly sand casting is done. So a lot of large parts and blocks and things, engine blocks, heads, large parts start out in this variety. So because they can be made cheaply for large materials with minimizing the machining time, because that's very, very expensive. So those can be pretty gnarly in terms of machining cost from scratch. So that's why those parts are typically cast. So you have the molten material coming in, and you have air escape paths coming out. And so you'll have different things typically referred to as like sprues that will be material that you may shave off at the end when you do final machining work. But you get the majority of the geometry of the thing, and you only have to do some final machining work, which saves you significant time and cost. Sand, the biggest reason is temperature resistant, because temperature, it can withstand temperatures over 1600 degrees, and it's inexpensive. It's also very easy to mold with. So there's a lot of ways to get the desired shape, and I'll see if this works. It may or may not. Wow, 240p. So there's a lot of things that we can do with those kinds of techniques, but you saw how quickly that changed temperature, even if the mold is preheated. It's very, very easy to have the material cool, and as it cools, it shrinks and creates all sorts of challenges for the material. So some of the other things that we have to keep in mind are the way that we can do lost wax type castings. There's also like lost plastic type casting. So this is something that has recently been done, especially with some 3D printing examples where they've done lost plastic casting. You 3D print something, you open up some specific channels, and we'll look at an example of that video as well to see what that looks like. You create a shape in something like wax or plastic, something that has a low melt temperature. It's usually something that has a very small volume, something that's a very complex shape. So things like jewelry or turbine blades that are done this way. But you can do that with, there have been some examples that I've seen where somebody did brass casting of some gears that were 3D printed, which was actually really cool. So there are some applications where that can be very useful. So you have wax stage, you have something like plaster of Paris around the wax pattern. The plaster hardens. Then the wax is melted and a hollow void within the shape of your part remains. So you elevate the temperature as you cure the plaster of Paris, and then so you want it to kind of cure first. Then you melt the wax, and then molten metal is poured in and allowed to solidify. So the same kind of process. So we'll see. I don't know that it'll play from here, but we can try. Hopefully it does.
Many machine parts are simply stamped or machined out of solid metal, but parts with complex shapes or thin walls can't be made that way. They have to be cast using a technique called lost wax process casting. It takes anywhere from a week to a month to manufacture a cast metal part, depending on its complexity. The first step is to inject wax into an aluminum die, which is essentially a mold whose cavity is in the shape of the part. This creates a wax model slightly larger than the finished part will be. They'll use this wax model to make a mold out of a ceramic material. That also has to be larger than a finished part because metal shrinks as it cools. Once the wax model is ready, they stamp on a code to tell the foundry workers what type of metal to use to cast the part. Next, using a hot iron, they attach wax components to create what's called a metal delivery system, channels that will funnel the molten metal into the mold's cavity. Next, they dip this wax assembly into a ceramic solution called slurry. They do this by hand to prevent imperfections that would cause defects in the casting. To strengthen the slurry, they coat it in a fine zirconium sand, then let it dry. A robot then keeps repeating the process with coarser sand until the ceramic shell surrounding the wax assembly is about 7 millimeters thick. This takes 5 days. Now the ceramic covered wax assembly is ready for what they call the de-wax. Workers place it in a hot steam chamber called an autoclave for 5 to 10 minutes. This melts the wax right out of the shell, creating a ceramic mold whose cavity is in the shape of the part. Once the mold has dried out, workers can then begin to cast the part. First, they put the cold mold into an oven and heat it up for 2 to 3 hours. This prevents the mold from cracking from the shock of coming into contact with molten metal that's a piping 1200 degrees Celsius. They pour the metal into the mold's cavity, then let it cool and harden at room temperature. That takes 2 hours for aluminum, 4 to 5 hours for steel. Once the metal has cooled and solidified, they break off the ceramic mold using a vibrating hammer. This takes about 5 minutes. They saw off the metal delivery system. Then grind the surface smooth. The final step is to make sure the part came out to the exact dimensions specified in the technical drawing. This is called sizing. Steel parts have to be heated up in an oven for sizing. Aluminum parts are sized cold. Technicians use a series of tools and presses to measure the part. If it doesn't meet specifications, it's either reworked or simply discarded. They use sophisticated equipment such as this optical comparator to check angles and radiuses, and this coordinate measuring machine to verify dimensions.
So as much as you guys would love to learn more about casting of chocolate and maybe casting of chocolate into your mouths, the dye process is a little bit different than that. So you start with typically something that's a lot higher volume. So you saw an example where they used a dye and injected the wax at the first stage. So there was a lot of steps in order to get to the end object there. A lot of extra material, a lot of materials that have to be melted back down and recaptured later. That creates a lot more workflow for the process here. So the low melting temperatures are really, really important for this process, because that way they can not have to have the dyes be made of something like sand that can carry the high temperatures. So that's why things like plaster of Paris kind of thing is useful for that sort of lost wax type. But you can also use ceramic molds and develop them in that same way. So continuous casting is like rectangular slabs or cylinders. Things that are going to be the same geometry can be done in a continuous or semi-continuous casting operation. So things that come out the other end and have cooled sufficiently to solidify. So there are some options to improve kind of the throughput there a little bit. So a little more anatomy of the sand casting as opposed to die casting. You have some different levels. The sand casting is a lot slower to cool, but you have and you have very low tensile strength, so you're going to have a lot more non-equiaxed crystals. So there's going to be a lot more variation because of that crystalline cooling path that we saw. So the actual mold itself, you have a feeder on the left, so material comes in at this side. You have a gate that controls the flow that's part of this runner. So material comes in, fills, the actual mold cavity. So this is going to contain the part itself in this small region. Then you have this is a bonded kind of sand. So think of it sort of like the kinetic sand stuff that's becoming popular for kids now. You have a parting surface or a split surface where the mold can be taken apart easily. So you have a couple sections of the mold. And you have a riser, so this allows for extra material. So the design is such that any air is always going to be pushed out the top to the riser, and then the material both at the feeder and the riser are where you're going to see the material shrinkage for the sand mold. So the die casting is a little bit faster to cool because you can actively cool the die itself, and you can also actively heat the die, so a lot higher tensile strength. So this works great for low melt or even high temperature. So cast iron and things that can be very high temperature, these are great for. You wouldn't want to try and die cast those. It just doesn't make sense. So size and complexity matter a lot. It's very expensive to make these big dies. It can be tens of thousands of dollars to make one of those single aluminum dies, believe it or not. So it's very, very expensive process. The number of castings required can also be important. The cycle time or the amount, the volume needed, all of those sorts of things go into this. The flexibility to be adapted to different forms is also going to be important. Operating cost per casting, so the mechanical properties, and then the quality of the casting, surface finish, porosity, voids, etc. All those things are also important. So the metal fabrication methods are there's a lot of these, so we won't go over zillions of them, but we'll cover a handful. Welding is a very, very common one. You have a filler metal that melts and fuses the base metal together. And then you have heat affected zones across those materials. So you do have something that is strong when joined, but it creates a new kind of weak point. And that's why a lot of times cracks happen at the weld region, because the microstructure has been changed and weakened in that area. So if you weld two heat treated things together, you have effectively unheat treated them and lost some of that strength that you would have had otherwise. So a lot of times those parts will have to be reheat treated for the final application. So the ferrous alloys, steels and cast irons, whereas the non-ferrous, copper, aluminum, titanium, magnesium, refractory and noble metals, those are all useful. So especially things like tungsten. Some of you have probably grown up almost without tungsten filament light bulbs altogether, which is pretty wild. But it's a really, really cool material. So there are some interesting materials being used. Especially now, there's carbon laminates or composites for instance, like a Boeing 787. You have about 50% of the materials are an advanced composite to give you really low weight and high strength. You have about 20% aluminum, so that's basically the structural frame inside. There's a lot of titanium for high strength and lightness, steel for the abuse areas, primarily landing gear, transfers into the rest of the frame, and then cloth and foam and other materials go into those. So that's excluding some of the that's probably also including any additional wiring and other things. I think they're also using a lot more fiber optic stuff now, so a lot more glass and things than there used to be. Onwards and upwards to processing, because I want to try and see if I can get through all of it with you guys today. And I think we're going to be on pace to be able to do that. So we'll be able to include maybe some other examples of some of these the annealing processes and things from someone that's actually doing the forging and heat treating process, which is pretty interesting. So we'll see if we have time for that. So some of the thermal processing, you're heating up to the temperature of annealing or T-anneal, and then cooling slowly. So you have a process anneal. You're trying to essentially undo the negative effects of cold working by recovery or recrystallization. And then stress relief. So this is going to be reduced stress from things like plastic deformation. This is why I want to try and get through the material to show you guys some examples of how this is actually done in materials to see what the stress relief actually does. So I'm trying to undo some of the stress from plastic deformation and non-uniform cooling, and then phase transforms and things of that nature, as well as normalization. So normalization of steels is important. It helps to, especially with large grains, you can then do heat treating that will allow for the recrystallization down to smaller grains that gives you some of that strength back that you need. So that normalization is a very common process and very necessary for a lot of steel applications, especially because anytime you undergo some kind of a process operation, you change something about the properties of the steel, and you change how it's going to behave. So a lot of factors to take into consideration when you go to do something. So full annealing is something that's used to soften the steel so that you get more, you heat it up into the range where you get those gamma crystals, and then you furnace cool it to obtain coarse pearlite. So you're cooling it at a moderate rate there. You're not doing a rapid quench or something like that, but you're cooling it at a moderate rate through a furnace to obtain some coarse pearlite. So you're not trying to obtain fine pearlite and go for really hard material, but you're making a softer steel by having coarser grains in the material, and so that will help to make things a little bit better. Spheroidizing is often for machining purposes. So you're trying to heat it just below the eutectoid point and hold it there. So that helps to kind of even out some of the grains and allow them better mobility at higher temperatures. That then makes machining a little bit easier because you're not necessarily undoing much of the hardening that has been done to the material, but you're evening things out so that you don't have harder points and softer points. That makes the machining a lot more predictable. So yeah, cooling slowly is almost always for this kind of thermal process important. So this is what a curve looks like. So full annealing starts with there's kind of a continuous cooling transform. So this is a mathematical curve that shows where there's a transition. So starting from the eutectoid temperature. So again, that's the lowest temperature at which you have a phase change with the material for any given composition. So that eutectoid temperature, just a little bit above 700, 747 C or whatever it was, for steels. Austenite and perlite here, there's a transition between these two. So a full annealing process looks something like this, where as it cools in temperature, this is a temperature versus time. So it's not temperature versus percent carbon composition. That's really important. If you cool it very rapidly, the perlite, which is P over here, are not going to form. If you cool it too rapidly, you'll avoid perlite altogether. If you cool it moderately, you spend a lot of time crystallizing in this region, where you're going to have more perlite, and then you'll condense farther. So the austenite, which is the softer of the crystals, is going to be in this region. So you have a couple different regions. So 50%, 50-50 ratio here, and then 0% is down in this region. So the more slowly you cool, and depending on how rapidly you drop from that, you can get farther and farther into this perlite region. But the idea is these are orders of magnitude here. So 10 seconds, 10 squared, 10 to the third, 10 to the fourth. So you want to cool very slowly in order to get that perlite formation to do full annealing. Quenching just drops the temperature like a rock through whatever region you're in. So you're not going to get the same degree of perlite formation. You're going to have a lot more austenite instead, which might be okay for some of what you're doing. And the tempering brings martensite, which is the martensite up here. Tempering then brings back in some martensite into the region, but you have to get up to this I want to say it's 210 or 215 C, somewhere in that region, that you then, just below where you start to form perlite, you start to form this martensite. And so that can bring you back some degree of ductility, and make it a little bit less brittle behaving when you temper it. And so so you've got heat treatment going on. So these are some examples from, I think actually from our furnace, that are 100% in the gamma phase or austenite. And as the door opens, 1 minute later, they're no longer necessarily glowing red. They're getting down below that emission. That emissive temperature range is in the hundreds of C region. So 100% in the austenite phase can be here, up above like 600 to 700. So somewhere in the range of 600 and above C is where you start to get that emissive glow. So it's very, very hot. For the lab that's coming up this week, this is the hardenability test that we're going to be doing. So we have a machine that allows us to do a Jomini end quench test. So we have a specimen that's heated entirely into this gamma phase field. So again, we're up into that 500 plus C range. So it's going to be very, very hot samples that then is going to be hit so it reaches that temperature and is left for a certain period of time. Then it gets set down into the end quencher, which is a rather loud machine, and it will cool off. And so the distance from the machined end, as it increases, the material that's cooled more quickly down below is going to be harder, and the material farther away from the cooled end is going to be less hard comparatively. So we're going to do Rockwell hardness testing on a flat ground spot on the material after it is quenched. And so that's where Tyler and the lab staff and John are going to be helping you guys make sure these materials are ready to go. But this is a really, really good end quench. So it's something that we can get into. The reasons for the hardness changes are because of where and how it's actually doing the cooling. So this is an example of the distance from the quenched end of the way that you might see the material. So very, very close to the end, you're going to see a rapid change. And so you're going to get as many measurements as you can at that cooled end. There's going to be a very rapid decline. And then you're going to see a lot flatter arc as you get farther and farther away, but it's going to continue to decrease. So here, the path that it's going to follow, so we're looking at the martensite, which is very, very hard stuff. And that's in that 210 and below region. So where we're converting our austenite to martensite phase. This is kind of the path that it follows. So it's opened, it cools down slowly within the furnace. And then, it starts to cool a little bit as we get it quenching. It's going to be pulling down that temperature pretty linearly overall, and it's going to go through this phase. So it's not going to get into as much of the perlite curve, but it is going to spend a lot of time growing martensite, and this is where most of that time is going to be spent in terms of actual cooling rate is going to be forming martensite. So it's going to very quickly, within on the order of about 10 seconds or so, get down below this 400 region, and then quickly get into this martensite, where most of the things that are going to grow in terms of time are going to be the martensite. Whereas here, as you start moving up, you're going to get a little bit of martensite and perlite together, because it's going to take a little longer for it to start cooling. So it's going to be time delayed. And so each direction, each measurement point, as you go farther, you're going slower and slower in terms of the cooling. You're taking longer and longer to start cooling from that edge all the way up to the top. And so more and more and more perlite is going to be forming. Less and less time is spent, because the slope is a lot less steep. A lot less time is spent forming martensite. So it has the perlite is higher tensile strength, but lower hardness. And that's that compromise that you have to make. So the more that you go, the more perlite you get, because the majority of the time is spent forming perlite, not forming martensite, just from primarily a time perspective. So influences of the quenching medium and the specimen geometry. So air and oil and water can be are going to be different. So air is a low severity quench. Oil is a moderate severity quench. So a lot of times oil quenching is used. And then water is a very high severity quench. It also runs the risk of corroding the surface. So you get surface scaling and all kinds of things that happen very quickly. So that's why oil is often used. So air quench, very low change in hardness, if any at all. Oil, moderate change in hardness. Water has a very high change in hardness. And that's why we're using that in the Jomini end quench as a medium. Geometry also plays a factor, right? Because not only does the heat have to go somewhere, but the heat has to escape, and it has to actually do something useful. That heat has to do some of the work. And so you have this center that is a lot warmer than the surface. So you have a differing rate crystalline formation throughout the interior. So the hardness, this is often why it's referred to as surface hardening, because the surface has a high cooling rate and a high hardness. The center has a low cooling rate and a low hardness. So there's a lot that goes into that as an example. There's a lot of things that this will do in terms of changing the way the material behaves. So the surface to volume, the surface area to volume ratio changes significantly how that material is going to behave. So everything has to be hardened and processed the right way. Alloy composition also changes the way that things can be hardened. So starting all the way at the left with a 1040, you can get a very high hardness, but the farther and farther distance from the end, something like a 4340 is not going to change that much in terms of hardness. If we saw a much lower, like a 1010 steel or something like that, it wouldn't have any change in hardness at all. It would just be somewhere down here as almost like a flat line. It wouldn't change. So hardenability for 5 different alloys with this 0.4 weight percent. This is a 5140. This is an 8640. And a 4140. So each of these are different materials. So the cooling rate changes as a function of distance from the end. So very high cooling rate down low, very low cooling rate toward the top. And so that 1040 has a dramatic change, and that's why we're using a sample more like that, if I remember correctly. So 4140 has a much less change because it has a higher native hardness, higher, it has the same carbon content, but some of the other components improve the hardness significantly. The alloy steels, so a lot more chrome, a lot more molybdenum and nickel. These are, they shift where the nose happens. So they shift where the perlite begins to form. Martensite's still at the same temperature, but in terms of the time it takes to get into that region, they allow martensite to be easier to form by making it harder for it to form perlite. And this is why these alloy steels are easier to be harder, to have them be case hardened. And so the exterior is hardened, and that allows for a lot better better cooperation for these. So there is a lot that goes into it for these alloys, and there's another mechanism in there too called precipitation hardening. These are this is thinking in terms of the molecular structure, particles impeding dislocation motion. So we'll try and show an example of what that looks like, because there are some examples of those. The aluminum copper system, so aluminum copper can be alloyed together. So you have a eutectic point here at the lowest liquid composition or lowest melting temperature from liquid. So you have copper and aluminum working together here in the theta, so the theta phase, and you have purely aluminum in the alpha phase. So alpha and liquid up here, and you have alpha and theta down here. So above this certain temperature, part of it is only one phase and only the other phase depending on the copper. So precipitation hardening is only possible in this narrow region. So what this looks like is at A, you're heat treating the solution. So you have this temperature, you bring the material up to this temperature for point A. B is a room temperature quench. So you bring down the temperature sharply. And what that does is retains the alpha solid solution. So instead of giving it time to become alpha and gamma at the same time. C is a reheat to be able to nucleate small particles for theta in that alpha phase. So a slight reheat and then cooling down in order to precipitate these so that they form copper nodules. So the copper can be alloyed in a few different ways. Magnesium aluminum works kind of the same way as this as well. Copper beryllium and copper tin. Similar kinds of ideas that can be precipitation hardened. So think of precipitation as an immediate quench in order to make sure that there aren't dislocations and other things propagated in the material. So let's take a look at what happens in terms of tensile strength and percent elongation. Maxima for these curves are slightly different depending on what is often termed as the aging of the materials. So the tensile strength is precipitation heat treat time, depending on how long it's heat treated. There's a variance in the tensile strength, so it can be pretty significant, almost double the tensile strength depending on the solution. So non-equilibrated solid solution, meaning they're just mixed up bag as cast kind of thinking there. And then a lot of small precipitate, so properly aged material, and then fewer large precipitates, meaning over-aged. And what that looks like in terms of, so this is tensile strength, this is the percent elongation. So again, depending on how long they're heat treated, so percent elongation, they stretch under that load pretty significantly at the beginning. As they're heat treated, they cut that percent elongation in about half, which is really, really important because there are a lot of applications where you don't want those materials to be moving under load, because that can tend to be a bad thing. That can tend to be how a lot of really catastrophic events happen, is the materials moving too much under load, too much percent elongation under a load can tend to cause failure in some other areas, which precipitates bad events happening. So you do have local maxima that occur in the tensile strength curve, and so the two different temperatures give you different precipitation curves. Similarly, you have minima on the elongation curves because those two have to behave inversely. If it's stronger in tensile strength, it's lower in percent elongation. It has to be opposite always. So a recap: ferrous alloys, steels, and cast irons. The non-ferrous alloys are refractories, noble metals, often good conductors, those sorts of things, lighter weight, special purposes for the non-ferrous alloys. The fabrication techniques, we talked a little bit, were forming, casting, as well as a few miscellaneous. Hardenability of metals is also hugely important. the ability to be able to be heat treated is key, and that increases with the alloy content. So the precipitation hardening is also very, very useful because it can strengthen something due to the formation of precipitate. So that's precipitating out the copper, leaving the small nodules and things, and strengthening with small grain structures the other materials, the aluminum or the magnesium. If it's a copper beryllium, you're trying to crystallize out the beryllium. And that way, you can also have aluminum and magnesium alloys precipitate hardened because of that slightly larger alpha phase that's available, as long as you do that quenching process. The refractory metals, really, really useful in a lot of applications, really high melting temperatures, and extreme physical characteristics. This is why tungsten works in filaments for light bulbs. It's a really impressive material. The mechanically dense and resistant to conduction, corrosion, all those sorts of things. Tungsten molybdenum heat shield would be very, very effective one, come to think of it. So that's a really good example. These are tantalum. That was the other one that I was trying to remember. Tantalum, tungsten, niobium, iridium, osmium, and rhenium. All are some of the examples of these. So they're resistant to high temperature. This is why things like iridium are also used in spark plugs. A lot of times you have to pay a lot more for them, but they tend to have a reasonably high durability compared to some other things. So there's a lot of practical applications of how to use these and how to use them well. So there's a stadium in Minneapolis. They're just in the roof that was built. There's some 11,000 tons. They have 989 foot long trusses. So that particular truss is pretty extreme. So that truss by itself is 1,700 tons. It's the height of that particular ceiling is about 215 feet or 214 feet above the playing field. And it took almost 250,000 hours for just the roof itself. So it's one of the heaviest pieces of structural steel, and it's more than 700,000 pounds. And it has a depth of 36 feet at its tallest point, and 16 feet wide and 197 feet long. So just a very interesting tidbit from the metal supermarkets, because I think they want you to buy a lot more steel to do all sorts of things. So a lot of really interesting things that come out of that. All right. So you guys have survived at least part of this. So let's check in real quick and see, A, how many of you are still alive, and then B, how many of you have questions, because we can recover things, or I can also find you guys some examples of some more details about how some of this process works. What are you guys' thoughts?
I mean, I always enjoy if we just do like some example problems, just to go over like the specifics of how this stuff works.
Yeah. The materials, let's see. I've got access to some of them, because a lot of these are I haven't had a chance to get in to the homework system and see how far along you guys are. But let me see if I can log in real quick and see where you're at. Because I know there's a few examples, so this is probably a good time for you guys to take quick advantage of your bio breaks and things like that. I'll see what we have available in terms of the course material. Let's see. I'm going to see what some of the example problems look like. So some of the questions are going to be things like identifying percentage compositions. There's going to be a lot of qualitative questions. Let's see, because a lot of these are not necessarily going to be heavy, like number crunching questions. A lot of them are going to be going back and looking at qualitative things, asking if you guys understand about annealing, those sorts of things. So there aren't nearly like a lot of written numeric problems in the same way. I'm trying to look through and see if there are actually any of them, because I think this chapter is like 95% or more conceptual in terms of the way the questions are structured and things like that. So there are, I'm trying to see if there's some examples looking at different crystallization aspects, cooling curves, stuff like that. Yeah, it looks like a lot of it is all conceptualizing. So it's a lot about grain properties, what role those play, those sorts of things. So this, at least in terms of like the homework and things of that nature, we're going to get a lot more into the actual sort of calculation of things in the lab. So you guys will have a separate lab handout for that. Because a lot of this, at least in terms of the way homework goes, a lot of that is going to be a lot of that looks like it's all conceptual questions. So a lot of that's for this particular chapter. There's not a lot of calculation. I'm looking to see if there's other assignments related to 11. It doesn't look like it. Okay. Yeah, it doesn't look like it. So yeah, that's probably the next best thing to take a look at is whether or not you guys have concept questions or something is like super duper unclear from what we covered, because that's going to help you guys more in terms of the homework and the workload, because you're not going to be like having to necessarily draw the cooling curve and show exactly where it is at each different point in time. A lot of this particular chapter is conceptual and getting to understand it. So any questions?
Really don't have any questions. Trying to take all that.
Yeah, it's a lot of material. And so this one, you might not have as many questions. So let me see if I can find an example. Let me see if I can find a good example. Because I know there's a few. Let's see. There's a couple. There's actually a bunch of really great examples. Let's see. Um, um, there's some good examples. I've used a couple of these in the past. I'm just looking for some specifics. Um, um, there's a young British chap that's actually a very good blacksmith that does a great job explaining what's going on. Let's see. Because there's a couple. He's actually done some examples. Drive home some things on a different note. Let's see. There's some folks that have managed to successfully do some forging with copper. And that's what I'm looking for right now. Because there have been some really, really awesome examples of those. Um, um, let's see. Here we go. I think it's this one. He's done a few of the non-ferrous metals. Yeah. He's done a few of the non-ferrous metals. He actually managed to do he did manage to do a copper nickel Damascus, and this one might be a great example actually, to show a few principles. So I'll do that as a really good example. Let's see. So that should be shared here. So this is actually probably reasonable stuff for you guys to be studying anyway. I'm going to turn this down just a little bit. But this is a really good example.
There's no sound.
I don't know if you can see the chat, but there's no audio coming through.
Can you guys actually hear that?
No.
No, we can't hear it.
Okay. It should be sharing with, it should be, yeah, it should be sharing with audio. Say that. It should be able to share. Let's see. Yeah, it should be. Sharing, and I'm looking to see if I have the option to enable audio, which I should. Interesting. Let me see if I can make any additional adjustments. Third party, okay. I don't see it. Yeah, that should be enabled. Interesting. Looks like okay, let me redo that differently instead, because that'll, yeah, let me do it this way. Yeah, okay. That should work. So prepare your eardrums. You might want to turn down your volume if you got headphones. Well, rest in peace. You've been warned.
I don't know why we caught it on fire. There we go. So now we've got this billet stacked up. We need to put it in the fire. The trick is, the forge is hotter than the melting temperature. Oh boy. Now, as I've said, I've never tried this before, but the basic understanding I have of what it is that we're trying to do here is get those pieces of copper and nickel so close to the melting temperature that when we hammer them or press them together, they'll fuse, just like with Damascus. Except I think that we're a lot more likely to melt these things than we are with Damascus pieces. So what I think I'm going to do is, just like when we heat treat a big sword, we're going to make the heat of the fire a little less aggressive with this piece of tube. So now that the tube is hot, into it we go with our stack of copper and nickel. Hopefully we don't melt it. I'm going to leave this camera pointing right at it in case we do. Please not make a puddle in the forge. Oh, there's a green flame. Can you see that green flame? You can't see the green flame. Okay, but I think we might be coming up to temperature. So it's starting to become a very dull red, just slightly incandescent. I think I'm waiting for the surfaces to become just a little glazy. Okay, it's coming up to a little bit of a light orange, which is soon going to be approaching the temperature at which we melt that copper. Let's have a feel with this little stick here. Doesn't feel tacky at all, and obviously, I don't know what I'm doing, but I guess I would feel it was a little tacky if it was ready for the fuse for the weld. Right, I'm going to change lenses and we're going to give this a go. So it's still a light orange, we're going to give it some light tap. It's a very glazed surface. Gently start giving it some light touches with the power hammer. It's now starting to turn to a dull orange. See what we can see from that. It's difficult to tell just from looking at it whether it's fused. I certainly know from my experience at Damascus, this doesn't look, you know, this doesn't look abnormal even if it was fused. I'm just going to take an aggressive rasp stroke just on the sides here and see if it comes apart at all by doing that. So I've not noticed any signs of it coming apart from an aggressive stroke. Try and poke a chisel in it. Well, it's certainly breaking apart the layers. It's not coming apart quite as easily as I'd imagine it would if it hadn't taken to any degree. I think it's solid enough to try and keep working. And I think that that temperature was not necessarily too cold, because I have a sneaking suspicion that it would move a lot more if it weren't fused at all. So I'm going to rasp off this corner, and we'll go straight back in the forge. But I'm not even concerned about the tube this time. It seemed like it was hot enough to not have to worry. Okay, I think we're about ready. Moment of truth. What happens if we turn it sideways? Wow! It looks like it stayed together. That's amazing! Right, let's drop it back in the fire and heat it up again. How cool is that? It kind of lights up in this weird way, and I can't tell if it's the flame or the copper doing something weird, but it's almost glistening. And then it stopped, right as I described it. There we go, look at that. Right, now let's try working it sideways, a good deal. Wow, it feels really homogeneous. This is copper and nickel, and we just fused it together. This is insane. It looks like, sadly, some slag from the bottom of the forge got stuck to it while I was hammering, and it made that big impression. I think a cleaner forge floor would be very handy for this operation. So I put a block of steel on the floor. Oh, and I missed it. I will heat it up on there, see if that keeps it a little cleaner. Right, let's forge it out some more. Uh-oh, that's not good. Maybe I'm being a little too aggressive.
The grains are being elongated, all in one direction, being stretched lengthwise.
At AHA, we know product managers shape the future. What you build changes lives for the better in ways.
So I took that piece of steel out of the fire. It was actually making it pick up even more debris from it. And instead, since I don't have any stainless, I just thrown a brick in there, so at least it stays off the dusty floor. Heats up really fast. Now it's got some heat in it. So a testament of how well it's held together is going to be twisting it. This falls apart when we twist it. We know it's not very good. And it hasn't stuck together, and we've got to change something up. If it stays together, then it could be a little bit more promising. So I'm going to get on here with a wrench and start twisting. Right, let's take another heat. It certainly stiffens up a lot as it cools. Oh no. It's not twisting in the middle now, it's only twisting at the top where it's mushing over from the wrench. All this material's just smushing and it won't hold its shape well enough to be able to twist it. It certainly looks super crusty. Doesn't look like it's very strongly held together, and the edges, they don't blend in the same way it blends in with steel when you forge weld the steel. Let's try some more twisting. Whoop, camera in the way. No, it just mushes it again. Oh boy, that's ugly. Try it one last twist. No! Uh-oh. Oh no, just rounded it. Oh well. That is crusty. Ugh. All right, let's flatten it down.
At every step, he's having to stretch and elongate those grains to forge these different materials together.
So that is attempt number 1 of Mekumegane. And how do I feel it went? Yeah. Is the best way I can describe it. Very, very crusty. So I have no idea if we're going to get anything from it. It's possible that it's just the outside layers where they didn't fuse, because of course, once we twist it, all those outside layers are surrounding the periphery of the material. And hopefully that means that once we grind this thing, we can expose solid fused material in the center. That is the hope.
The brain structures, how they impact performance and behavior, all of those things. So those are important to understand. But he's actually come up with a nice
is
material.
Pretty freaking awesome. Copper and nickel. It's actually only gone and fused together. It looks awesome. In fact, it's just so awesome that now that we have some validation on our process. We're gonna heat the forge up. Woo-wee. And we are gonna make up one big, glorious, expensive stack of copper and nickel. Let me tell you, nickel is expensive. Holy granola, that stuff is not cheap. So we've now got the scale cleaned off, we've got it forged out, and so now that means that it is time to open it up and see how the pattern looks inside. Woo-hoo-hoo! Ow!
Listen to music without.
Oh my goodness! Oh! Ooh, yeah. That's kind of cool, huh? Kind of cool, yeah. I think that'll work.
Manufacture the billet into a further forging process.
Check it out! I think it's fused! I was terrified. I was concerned that it only fused because we had copper the first time, but I really think it's done it. I think it's together, and look at how beautiful that pattern looks. I think I found that the key is to work a little bit on each side. It's not to work a lot from one side, but just take a few blows and then turn it. A few blows and turn it. So I have this full bar, and I am shocked and surprised that it wasn't cracked the whole way through. But the pattern on this piece is just incredible, as you've seen. At this stage, it's on biased W's, which means stacking this up 4 ways into a square will make an explosion pattern. We're gonna leave that for another day. I'd love to hear what it is that you'd like me to make from this piece of Mikume Gane. I've also got these cool offcuts. Look, it's my hair. And of course, attempt number 1, that beautiful piece of flat stock of Mikume twist. So drop me a comment and let me know what you want me to make from it. And of course, look at that shirt. This is the process tee. It just came in for me today. It's got forged.
All the things like comment, subscribe, etc. You get the idea. The point is, in order to keep those grains moving against and across each other in each circumstance, what he actually has to do is he has to continually keep that at elevated temperature and then drop the actual he has to continually hammer and forge from all these different directions and keep those grains moving, but keep the temperature elevated so all those molecules have enough kinetic energy to get past each other. So even though the materials that he's forging are all different kinds, he has to have some very heavy, durable, high-grade steels on his equipment, in his anvils, his hammers, all of those things. So all of these different materials come into play in one very interesting way. So you have a lot of different materials being used, and that particular power hammer has had significant abuse over the years. So a good guy to follow and find information from in the materials applications, because he talks a lot about the materials and how they behave, why they have to be heated and heat treating and all sorts of things. So he has a lot of great informational videos on his channel and things that will help you guys learn from another perspective why this stuff is important, why you need to understand how the material is going to behave before, during, and after processing, and what you can do to recover and manage some of those things. So we're about out of time for today. Any final questions from you guys? Or you guys think you're sort of making sense? Have we, on a grand scale of clarity, are we at like where holy water is at the top and like at the very, very bottom is dirt with no water? There's like mud, there's like OG Gatorades in there, then there's like Crystal Light, and then there's like flavored water, and then there's holy water at the top. Where are you guys at on that scale? Where do you guys think you are?
I'd give you a flavored water.
Flavored water? That's pretty good. Where's everybody else at?
What was the options again? You said flavor water. You said spring
Oh.
water.
Yeah, there's like flavored water. The very top is like holy water. That's like perfect clairvoyant understanding. Then there's like OG Gatorade flavors. Then there's like mud. Then there's like at the bottom is dirt with like no water at all. So where are you guys at on that scale?
I'd probably put myself in like flavored water.
Okay. So I see some Gatorade. I see some flavored waters. Anybody else?
I feel like I'd be okay.
Gatorade is okay. Gatorade is okay. An entire chapter in a day. Gatorade's not bad. All right. There goes Axel being different every time. Sparkling water. There you go. All right. Good. All right. Well, I've got a couple minutes before I jump into the next class. I will see you guys in some capacity in lab, where we're going to be doing the Jomini end quench test this week. And then we're working on details of the rest of things. So hopefully this is helpful to you guys. And I'll get links to YouTube where this will be stored and all of those things. So I'll get all of that up for you guys. So with that, I guess I'll see you guys later this week.
Have a
Thank
good day,
you.
Professor.
Yep.
Thank you, Professor. Have a good day.